Hello all, welcome to IT and Gate classes. Today we'll be discussing questions from theory of machines that have appeared in Gate 2021, right? Both forenoon and afternoon papers. We are not taking up questions from vibrations because vibrations will be dealt as a separate subject. Okay. So in total there were 7 questions. The level of the questions went from easy from moderate. All were conceptual questions, good questions, right? But all were within the syllabus. So let's start. This is the first question, which is from mechanism, Whitworth quick return mechanism. You're asked the quick return ratio for the mechanism, right? So the Whitworth quick return mechanism shown in the figure with the link as follows. The length of the links is given. OP is equal to 300, OA is equal to 150, and AR is equal to 450. Sorry, 160. AR is equal to 160, and total length RS is equal to 450 mm. Okay. So let us first understand how exactly the Whitworth quick return mechanism works, right? Then we'll be able to understand what is the quick return ratio. So basically you see this is the crank. So the crank rotates full circles, right? It rotates full circles, right? So this is a slider. The slider slides in the rod RP. The slider slides in the rod RP, right? It can slide. The slider can slide in the rod RP. Okay. So basically RP length is not constant. RP length is not constant. RP can keep on changing, or you can say AP length. AP length is also not constant. AP will keep on changing. Okay. This is the value of AR, right? AP will keep on changing. AR is equal to 160, right? And RS is equal to 450. This is RS is equal to 450. Okay, so the point P will keep on changing, keep on moving. The slider will keep on moving on the rod RP, right? So you have to understand first that when and okay, so this is the ram, this is ram. So there will be a cutting tool attached on the ram, right? So when the ram moves forward, it is called the cutting stroke. Cutting stroke. Because when the ram moves forward, it will cut the workpiece, right? Whatever it might be safer, it might be planar, right? So whatever the workpiece, it is making a cutting motion, right? That is why it is known as cutting stroke or the forward stroke, right? Or the forward stroke. Then the ram will move backwards. That is the return stroke. Return stroke. Okay, so let us try to see what is the maximum stroke length, right? So let us try to understand. So when the point P is somewhere here, the slider is somewhere here. Let me say this is the point P1. When the slider is somewhere here, and this is the link OS. Okay, OP1. The link OP1. So this link OP, it is somewhere here. Okay. In that case, what will be the position of R? So the point R will be somewhere here. Let me say this is R1. The point R will be somewhere here, right? And you can see the R1S will be somewhere here. So somewhere here will be the slider. The slider will be somewhere here. So slider will be at its left extreme. The slider will be somewhere at its left extreme, right? Right, because RS will be a straight line, right? RS will be a straight line, right? So the slider is somewhere here. The slider will be somewhere here, right? And the point S will be somewhere here, and this ram will be at its left extreme. Now, as soon as the link OP1 starts moving from this side, the ram will start its forward cutting stroke, right? It will start its forward cutting stroke. And when the ram reaches, when the link OP, it reaches somewhere here. Link OP, it reaches somewhere here. This is the say P1, P2. Let me say this position P2, and R will be somewhere here, R2, right? R will be somewhere here, R2. So in that case, what is going to happen? The RS link, you can see the RS link will be somewhere like this. So here will be the ram, here will be the ram, right? And the ram has completed its cutting stroke. The ram has completed its cutting stroke, right? Means the ram is at its rightmost position, the right extreme, right? So basically when the crank moves from P1, the crank moves from the P1, OP1 to OP2. When the crank moves from OP1 to OP2, the point R will move from R1 to R2, right? Will move from R1 to R2, and the ram will complete its cutting stroke, right? So basically this is the cutting stroke angle. If you see this angle is known as the cutting stroke angle. We denote it as beta, right? This is the cutting stroke angle, right? Then when the crank will move from OP2 to OP1 back, right? OP2 to OP1, it will come from here to here. So what will happen in that, the ram will move backward and it will execute its return stroke and it will come to its original position. It will come to its original position. So this angle is known as alpha. This angle is known as alpha. That is the return stroke angle. Return stroke angle. So what is quick return ratio? Quick return ratio is equal to beta divided by alpha. Quick return ratio is beta divided by alpha. So why the quick return ratio? Quick return ratio because see, while cutting, it is carrying out the cutting very nicely, properly. It is in slow speed, properly it is cutting. So while the return stroke, where it does not have anything to do, it is not walking on the return stroke, right? So it is coming fast. So return stroke, you see, it is traveling only alpha, only angle alpha. Forward stroke, it is traveling angle beta, right? Definitely the return stroke is faster than the forward stroke. So quick return ratio is how fast is the return stroke than the you can say the forward stroke, or you can say it this way, what is the ratio of time taken, right, in the forward stroke and the return stroke. So basically you have to calculate angle alpha and beta, and we can take the ratio to find out the quick return ratio. Let us see. So basically this is the position. So when the crank is at OP1, the ram will be somewhere here, it is left extreme. When the crank is at OP2, right, the crank will be at its right extreme. So this is the forward stroke or the cutting stroke, right? And then when the crank moves from OP2 to OP1, we will execute the return stroke, right? So cutting stroke angle is beta. Cutting stroke angle is equal to beta, and return stroke angle is equal to alpha. Return stroke angle is alpha. So how to calculate alpha beta? Very easy. Dimensions are given. It is already given that OP1 is equal to 300 and OA is equal to 150. It is given. Let us see. OA is 150, OP is 300, right? So what will be alpha? Cos alpha by 2 is equal to, I can say 150 by 300, that is half, means alpha by 2 is 60, means alpha is equal to 120. So the return stroke angle is 120 degree. The whole angle alpha, this alpha I am talking about, this alpha I got it as 120. This angle alpha is 120 degree, right? So if alpha is 120, what will be beta? Beta, I can say it is 360 minus, what will be beta? Beta is equal to 360 minus alpha, that is equal to 240, right? Beta is 240 degree. So what is the quick return ratio now? Quick return ratio is beta by alpha, that is 240 by 120, that is equal to 2. Right? So this was very simple question. Even you didn't have understanding of the quick return motion properly, still you could have made out. Okay? Only thing you have to do is you have to imagine what will be the extreme position. It is very clear that when the point P, it's very clear that when the point P will be somewhere here, the point R will be somewhere here, right? The point R will be somewhere here, right? When the point P is somewhere here, right? So this will be the left extreme, right? And when the point P is somewhere here, the R, right, it would have moved from this position, right? It would have moved from this position and it will come somewhere here, right? R will be somewhere here, right? So that will be the right extreme. So this can be imagined without much problem, right? So if you can do that, right, if you can do that, you can easily come up with the answer. Okay, Let us move on to the second question. Again, the second question is a very nice question, right? It is from the balancing of reciprocating masses, right? All of us know what is the, let us first read the question, right? Considering a reciprocating engine with crank radius r and connecting rod of length l, the secondary unbalanced force for this case is equivalent to primary unbalanced force due to a virtual crank off, right? So it is being asked, so if the secondary unbalanced force is equivalent, means is equal to the primary unbalanced force, right? If we consider the secondary unbalanced force to be equal to primary unbalanced force, what will, right, the radius and speed of the engine, if you by considering a virtual crank, okay, virtual crank means imaginary crank, right? Suppose the secondary unbalanced force has to be equal to primary unbalanced force, right? Definitely they are not equal, right? They are not equal, they are different. But suppose we consider them to be equal by considering a virtual crank, at the secondary unbalance, right? So what will be the radius of the crank and what will be the speed of the engine? Okay, let us try to find out. So it's very simple. You'll simply equate the primary unbalance and secondary unbalance, then we'll find out the crank, right? So we all know that for a reciprocating engine, the unbalanced force looks like something like this, right? M r omega square cos theta, m r omega square cos 2 theta by n, right? This is the primary force, which is large, right? This is the secondary force, which is small, right? Generally we neglect secondary force in balancing in slow speed engines, right? Okay, we'll not go into those details. We'll just stick to what the question has asked us, right? We know obligatory ratio. What is obligatory ratio? It is L divided by R. This N we are talking about, this N is the obligatory ratio, that is L divided by R, right? Let us simply do, it is saying that the primary unbalance and secondary unbalance are equal. So let us simply equate them. Right? Let us write N. Okay? I am considering the secondary unbalance now. Okay? I am considering secondary unbalance now, right? The secondary unbalance force m r omega square cos 2 theta by n. N I am writing as L by R. So here R becomes R square, right? So I can rewrite it as m r square by 4L 2 omega square cos theta, right? So if you see here, if you compare this with the primary unbalanced force, can I say that the radius of the virtual crank will be r square by 4L? The radius of the virtual crank will be r square by 4L. And what will be the angular speed? Angular speed is omega here. Here, what is the angular speed? Angular speed is twice. Right? So what will be the answer? Answer is r square by 4L rotating at twice the engine speed. Right? So why did I arrange it like that? You might have the confusion. Why did I actually arrange it this way? See, that hint you have to take it from the options. If you see the options, what are the options? Right? L by 2, R by 2, L square by 4R, R square by 4L. So you have to see the options. How can you manage? R square is already there. L is already there in the denominator. R square is already there in the numerator. So what to do? So let us multiply it by 4. This is what the option has, right? Let us try to make it r square by 4L. So once you do r square by 4L, where will 4 go? 4 you can club it here. So we'll come up with the answer. So definitely in objective questions, you'll also have to go through the answers and see how to come up with the right solution. You can always take help from the options. Okay, let us move on to the next question. This is again a very nice question, right? This question from velocity and acceleration analysis, I center, right? What you are asked here, right, is consider a mechanism shown in the figure. There is a rolling contact without slip between the disc and the ground. So this is the disc and this ground. So there is a rolling contact between that, right? Select the correct statement, right? Basically, they are asking you the instantaneous centers. Which points are instantaneous centers? They have 5 points: P, Q, R, S, T, U. 6 points are there. P, Q, R, S, T, U. So these are the 6 points. They are asking out of these 6 points, which are the eye centers. So basically in this question, you have to find out the eye centers. Let us see, right? So how many eye centers will be there? In total, how many eye centers will be there? There is a 4-member link. You can see link 1 is a fixed link, right? Let me see here. Link 1 is a fixed link. link 2 is this crank, link 3 is this connecting rod, link 4 is the slider, this disc, right? So 4-member link. So number of eye centers is equal to 4 into 4 minus 1 divided by 2, that is equal to 3 into 2, 6. There are 6 eye centers. What are those? Can we see the eye centers? Can you see the eye centers? I12, I13, I14, I23, I24, I34. These are the 6 eye centers. Let us see which eye centers we already know. We know 1 and 2, the turning pair. So this is we know. We know 2 and 3, again this is a turning pair. 2, 3 we know. We know I14. We know the disc is rolling. A disc rolling over a fixed straight line. So the point of contact is the instantaneous center of matter. Instantaneous center. Okay. I14 I know, right? I know I43, right? Because again it is a turning pair, right? Basically what I don't know is I24. 14 I know. I know. Basically I know 14, right? This is I14. Basically what I don't know is I24 and I13. These are the 2 eye centers I don't know. I have to find this out, right? So how to find it out? Using the circle diagram, right? We'll draw a circle, we'll plot the 1, 2, 3, 4, right? We'll plot the links 1, 2, 3, 4. So if to find I13, right? To go from 1 to 3, we have 2 options. First go from 1 to 2, then go from 2 to 3. 1 to 2, 2 to 3. Or what you can do, you can go from 1 to 4, then 4 to 3. 1 to 4, 4 to 3. 1 to 4, 4 to 3, right? So we'll join these 2 lines 1, 2, 2, 3 and 1, 4, 4, 3. What is 1, 2? This is 1, 2 and this is 2, 3. 2, 3, this is 2, 3. So 1, 2, 2, 3 will join it, right? And then we'll join 1, 4, 4, 3. 1, 4, 4, 3. 1, 4, this is 1, 4, this is 4, 3. We'll join it. So the point of intersection is I13. The point of intersection is I13, right? So we have got this point as U point as I13, right? Next is we have to find out, we have already found out this, we have to find out I24. So if you want to find out I24, how to find out I24? So if you want to reach from 2 to 4, there are 2 ways. 2, 3, 3, 4. Go from, I want to go from 2 to 4. So go from 2 to 3. Then you go from 3 to 4. Or what you can do is 1 to 1, 4. So you go from 1 to 1 2 is same as 2, 1. So 2 to 1 and then 1 to 4. Right? So we'll join these 2 lines. 1 to 1, 4 and 2, 3. 3, 4 will join it. Right? Where is 1, 4? What, this is 1, 4. Right? Where is 1, 2? This is 1, 2. So this line is 1, 2, 1, 4. Right? 2, 3, 3, 4. 2, 3, 3, 4. This is 2, 3. This is 2, 3. And this is 3, 4. Right? So we'll join these 2. So the point of intersection is nothing else but the eye center I24. So this way we will plot all the eye centers. This way we have plot all the eye centers, right? So we can see that all the points are basically some eye center. All the 6 points. P, Q, R, S, T and U. All the points are representing eye centers. So what will be the answer? D. P, Q, R, S, T, your instantaneous center of rotation. All the points are representing instantaneous center of rotation of the mechanism. I hope this is clear. See, these questions are conceptual, okay, but nothing is hard, right? It is even below moderate. Right? Again, here we have a very nice question. This is a question from gear trains. Gear trains are very important. All of you, make sure you do gear trains properly, right? Every paper will consist a question from gear train, at least 1 or sometimes even 2, right? Epicyclic gear train, compound gear train, simple gear trains, right? Finding out center distance, finding out modules, all these questions are very, very important. So do practice adequate questions, right? Questions are easy, okay? It is not hard. Okay, so let us see. A power transmission mechanism consists of a belt and a gear train as shown in the figure. So we have attached a belt, okay? So this is the driver. this is the driver, and the driver is rotating anti-clockwise with a RPM of 2500. Okay, so this is this driver is 1, if I say, so it is rotating 2, right? 2 and 3, or what I can say is this is not, this is 1, and then this is 2, and this is 3, right? So basically the driver 0 is rotating the gear 2, this pulley 2, this is not a gear, this is a pulley, right? 1 is pulley. So 1 and the gear 2 are compound, they are on the same shaft, mounted on the same shaft. So rotation of 1 and 2 will be same, right? 2 is thereafter externally connected to 3, so 2 is rotating 3. So 2 is the bigger one, please remember, the 2 is the bigger one, right? I hope I have used the same notation. Yes, I have used the same notation, right? So 2 is the bigger one, so 2 is connected to the 3, right? So the 3 rotates, right? So the 3 rotates, 3 and 4 are compound, so they will have same angular speed, right? And then 4 is connected to 5 externally, 5 is connected to 6, so 5 basically becomes the idler gear, 5 becomes the idler gear, right? Then 6 and 7 are on the same shaft, the rotational speed of 6 and 7 will be same, right? So diameters of pulleys of the belt drive and number of teeth of the gears from 2 to 7 are indicated in the figure. It is indicated in the figure, right? The speed and direction of rotation of the gear 7. So what is the speed and the direction of rotation of gear 7 that is being asked, right? So let us go start, right? So for the belt drive, I can simply say the N1 by N0. Okay, the speed of the driven by speed of the driver, it is opposite to, it is the ratio of the diameters. Okay, it is reciprocal of the ratio of the same diameters, right? So if it is not here, not will come here, right? N1 by N0 is equal to D1 by D0. You can substitute the value of N0, right? D1 D0. I know D1 is 150, D0 is 250, N0 is 2500. We'll get the value of N1 as 1500 RPM. No issue with that, right? So basically gear 2 is now rotating with a gear 1, because gear 2 and the pulley 1, they are on the same shaft. So I can say both will have the same rotation, 1500 RPM. Now for the belt drive, it is an open belt drive, then the directional rotation will remain same, right? It is rotating anti-clockwise. So if it is pulling it this side, so this will be pulled this side, right? So direction will remain same. Okay, so if N1 is the N0, the driver pulley is rotating anti-clockwise, finally the driven pulley will also rotate anti-clockwise. Okay, now gear 2 and 3 are connected. The number of teeth on gear 2 is 18, number of teeth on gear 3 is 44, right? So N3 by N2 is equal to T2 by T3. So I can find out N3 from here, like 1518 by 44, that is 613.66 RPM. Now the rotation will reverse, right? Because they are externally connected. So it is anti-clockwise, so this becomes clockwise, right? So the rotational speed of 3 and 4 will be same because they are in the same shaft. So N4 is also 613, right? Then you can proceed on to and finding the speed of N5. N5 by N4 is equal to T4 by T5, right? So from here you can find out N5, 613 into 15 by 33. Number of teeth on 5 is 33. Teeth on 4 is 15. Teeth on 4 is 15. So it becomes 278.925 anti-clockwise. Again, the direction reverse. So 5 is connected to 6. N6 by N5 is equal to T5 by T6. Right? So from here we'll get the value of N6. N6 is equal to 278, 33 by 36. 33 is the number of teeth on 5. 36 is the number of teeth on 6. So this is the value of LPM of N6. And N6 and N7, they are all connected to the same shaft. So both will have the same angular velocity, same RPM, right? So they are externally connected. So since this was anti-clockwise, this will become clockwise. So answer is 255.68 clockwise, right? So let us see what option we have. 255.68 clockwise. So answer is A. What is the answer? Answer is A, 255.68 RPM clockwise. So again, this is a very simple question. Yes, you can also use the concept that velocity ratio is equal to product of the number of teeth on the driven by product of number of teeth on driver, right? Yes, you can do it that way also, right? But okay, that formula already you know. Okay, if you have attended the classes, you know you can directly use that formula. But you have to find out which one is the driver, which one is the driven. So do not make mistake. This is a simple basic approach. Basic approach always is the best approach. Instead of remembering lots and tons and formulas, yes, definitely reduces the time it takes to solve the equation, but definitely you can practice that. If you practice through that formula, you can do it, but basic method is always the best method. Okay, fine. So let us move forward. This is a question from governor, right? This is a question from governor. This is the first time that a question has been asked from governor, right? So stability of the governor has been asked, right? So these are the controlling force diagrams, right? On the y-axis it is controlling force, on the x-axis it is radius of rotation, right? So basically this straight lines are for spring control governor. Which is the spring control governor you've seen in class? It is the Hartnell governor, right? Hartnell governor is a spring control governor. So the controlling force diagrams are straight line, right? There are three lines. Right? So one of them represents stable, one of them will represent unstable, right? I will tell you, okay, what is a stable, unstable, isochronous, right? If the radius increases and speed also increases, and radius decreases, speed also decreases, then it is called a stable governor. If radius increases, speed decreases, radius increases, radius decreases, if radius decreases, I'll do it again. Suppose the radius increases, radius of the governor increases, but the speed also increases, and speed also increases. And when the radius decreases, speed also decreases. Such kind of governor are called stable. Stable governor. Now, if radius increases, sometimes the governor's design of the governors might be flawed. If the radius increases, speed decreases, and radius decreases, speed increases. That kind of governors are called unstable, right? And there is a third category. Radius increases or radius decreases, it does not matter and remains constant. So this kind of governors are called isochronous or neutral governor. Isochronous or neutral governor, right? So let us try to find out, okay? Let us try to see here how we can say if the speed increases or decreases, right? If you can draw two lines, okay? I'll give you one example, okay? एक example जल्दी करते हैं. Let us draw two speed lines, okay? Let us draw two speed lines. This is one speed line and this is one speed line, okay? N1, N2, N1, N2, or R1, R2 are given. Let us draw the speed lines passing through R1 and R2. So this is R1, this is R2. Okay, so basically this is N1 and this is N2. Okay, here the N2, because the slope of N2 is more, so N2 is greater than N1. Okay, so let us see for the curve P. Let us see for the curve P. Okay, you can all can see the curve P, right? So basically this is R2, this is R1, right? So we can see that R2 is smaller than R1. R2 is smaller than R1. So what has happened here? When the radius increases, or let me say radius decreases from R2 to R1. When the radius decreases from R2 to R1, increases from R2 to R1, you can say it this way also. If the radius increases from R2 to R1, so the radius is increasing when we are moving from R2 to R1, right? So what happens to the speed at R2? What is the speed? N2. Right? And the N2 speeds moves on to at R1. What is the speed? N1. and we have already seen that n2 is greater than n1. So what happens? The speed actually decreases. Speed actually decreases. When the radius increases, the speed decreases in this case, right? So I can say, what I can say, that this P is representing unstable. Okay. What is the equation of this kind of line? Equation of this kind of line can be given as controlling force is equal to A my R minus B. Okay. Next time you might, instead of the graph, you might given be the equations. This kind of equations have also been asked in other exams. FC is equal to AR minus B. It is representing the unstable, right? Similar kind of exercise you can do it for this one Q. If you see the Q, so this is the speed line N. Okay. It does not matter what is the radius R, R1, R2, the speed remains constant. The speed remains constant. So controlling force curve is coinciding with the speed curve here, right? So what is the equation for this kind of curve? The equation for this kind of curve is Fc is equal to AR. So Fc is equal to AR, it represents the neutral or isochronous governor, right? So let us see the third line R. Focus on the third line R. Okay, this is the third line R, right? If you see the speed line, if you draw two speed lines N1 and N2, let me draw two speed lines N1 and N2. ठीक है ना? एक N1 हो गया, एक N2 हो गया. ठीक है? Let me say this is N2, this is N1. ठीक है? You can, N1 is greater than N2. Why? The slope is greater. ठीक है? The slope of N1 is greater. So you see, at a smaller radius, you have the smaller speed. At a greater radius, you have greater speed. So I can say when R increases, speed also increases. Where R increases, the speed also increases. At a smaller radius, R2, we have a smaller speed N2, and a greater radius R1, we have a greater speed N1. So as the radius increases, radius of rotation of the governor increases, the speed of the governor also increases. So what is that type of governor known as? That type of governors are known as the stable governor. So what is this? This is a stable. And what is the equation of this kind of governor? Fc is equal to AR plus B. Okay, this isochronous or neutral, right? So you have to also remember the equations. Next time, this time they have given the graph. Next time they might actually give you the equations. Okay, fine. So which is the right option? P is unstable, Q is isochronous, and R is stable, right? Option A. Let us move on to the next question. Yeah, I've already given you this, right? The stable, isochronous, and unstable, right? You can see this. Okay. Let us move to the next question. Okay, this is a very nice question. It is from Flywheel, right? Flywheel. It's a very, very nice question. So let us try to see what does this question say. The torque provided by an engine, this is the torque given. Okay, T theta is equal to 12,000 plus 2500 sine 2 theta, where theta is the angle turned by the crank from inner dead center. Okay, you know that. The mean speed is given 200 rpm. Mean speed is given 200 rpm. It drives a machine that provides a constant resisting torque. If variation of speed is 0. Plus minus 0.5. So you are given the value of CS. You have given the value of CS, right? Torque is given. Torque is given. Then you are given the speed. N is given is equal to 200 rpm. And you are given the value of CS. What is CS? CS equal to plus minus 0.5%. So I can say this is equal to plus minus is equal to 0.5 divided by 100 into 1. Percentage sign, if you remove it will be 100. So basically this is 0.1, right? Okay, so what to do here? You're given what exactly do here. So you're required to find out minimum mass moment of inertia of the flywheel. So there is only one equation, delta E is equal to I CS omega square. Okay, you are given CS, you are given omega, right? You're required to find out I. So what you have to do, basically you have to calculate delta E max. What is the maximum fluctuation of energy? What is the maximum fluctuation of energy? That is what you have to calculate. If you can calculate delta E max, right, you can actually calculate I. So this is a very good question. Similar kind of questions have appeared before also, right? So you need to calculate delta E. So what is the procedure to calculate delta E? Okay, we'll go step by step. We'll go step by step. Let us see the procedure to calculate delta I, right? Now, torque is given, right? N is given. CS is equal to plus minus 0.5. So it is equal to 0.01, right? So you need to calculate I. First, let us see what is the cycle time, okay, of this torque. What is the cycle time of this torque, right? So cycle time, how to calculate the cycle time, right? Very easy. What is the cycle time of sine theta? We have already done this in class, right? So we will not do it again. So what is the cycle time of sine theta? So cycle time, matter time period. Cycle time, I mean to, by cycle time I mean time period. So what is the time period of sine theta? The time period of sine theta is 2 pi. So what will be the time period of sine 2 theta? We'll divide it by 2, because the coefficient of theta is 2. We'll divide the period by 2. So it becomes 2 pi divided by 2, that is equal to pi. So the cycle time or the time period of this function is from 0 to pi. So after pi interval, it will repeat itself. After pi interval, it will repeat itself. So it is a sine curve. It will look like this. So after pi, it will again repeat itself. After pi, it will repeat itself. After pi, it will repeat itself. Right? Okay. So why is the cycle time required? The cycle time is required so that you can find out the work done. What is work done? Work done is the integration. Work done in one cycle. Work done is one cycle is the integration of this t theta. Right? So if you integrate this t theta from 0 to pi, if you integrate this theta from 0 to pi, integrate this. I'll not go through the integration now. It's a very simple integration, right? So it is equal to 12,000 pi. So what is the T mean? We know that T mean is equal to work cycle divided by cycle time. T mean is equal to work done in one cycle divided by cycle time, right? It is 12,000 pi divided by pi. Cycle time is pi, so it is equal to 12,000, right? So you need not worry, even if you didn't know how to calculate this, right? It is important because see, 0 to pi, even if you have considered the cycle time or time period as 0 to 2 pi, you would have come up with the same answer because you're dividing it by cycle time, right? But it wouldn't have been the case if it was the cycle time is 0 to say 2 pi by 3 or 3 pi by 4. In that case, it would have been difficult, right? So you should always know how to find out the cycle time, right? So work done in a cycle is a integration of the cycle time t theta, right? And you will get it, right? And T mean is equal to work cycle divided by cycle time, right? So this is what the curve look like. Okay, and this is the T mean line. So T mean line. So we have to first see where does the T mean line, there's 12,000, it intersects with the T theta. T mean 12,000, right? Where does the T mean line, it intersects with the torque, right? So for that, we'll simply equate. See, this is a general procedure. This is an easy question. You might be able to make out even without doing this. But this is a general procedure. You can follow this procedure to solve any kind of question of this type, right? So always follow this. You should know the procedure properly. So even if the question that has appeared is hard, this is a moderate level question. Even if the question is hard, you'll be able to solve it. That is the point, right? So when you do t theta is equal to t mean, right, you can equate this to 12,000 will get cancelled out. So sine 2 theta is equal to 0. So you can see 2 theta is equal to 0 pi 2 pi. So I can say theta is equal to 0 pi by 2 pi. So these are the points where the t theta and t mean line will intersect. So you can draw the curve now. And this is the curve, right? So first point of intersection is 0, then you have intersection at pi by 2, then you have intersection at pi, right? So basically, what is delta E now? This is delta E. Anything above the T mean line is delta E, right? Or below the T mean line. Since cycle contains only two humps, one upward hump and one downward hump, right? Both the humps will be equal. So delta will be equal, E will be equal. You calculate the area, you calculate this area or this area, both of them will be same. You calculate whichever area you want, both of them will be same, right? And equal to delta E max So let us calculate this area. So how to calculate this area, right? So it is simply t theta minus t mean integration from 0 to pi by 2. So basically this is t theta. The green I am representing is t theta, right? The blue is t mean. So t theta minus t mean integration from 0 to from 0 to pi by 2. This is what I have done, right? So when you subtract this, you will only left out to 2500 sine 2 theta. 2500 is constant, will come out 0 to pi by 2 sine 2 theta. You integrate it, you'll get it as 2500. So what is delta E now? What is the delta E? That is equal to 2500, right? So delta is equal to CS I omega square. You substitute the value. Delta is equal to 2500 I omega square. Omega is equal to 2 pi n by 60, right? So what is the value of I? I will be 569.93. All the units used were in SI units. We have not used anything else. So basically the answer will be in SI unit, kg meter square. 570 kg meter square. So this was again a good question. This is a moderate level question. Okay, if you have practiced this kind of questions earlier, because you must have practiced, because similar question have been solved in class, similar type of questions have been asked previously. So if you have practiced them properly, this question wouldn't have been any difficult for you, right? Okay, let us move to the last question. This question is from gyroscope. Very simple question. Let us see. Very nice question. The figure shows an arrangement of heavy propeller shaft in a ship. The combined polar mass of moment of inertia of the propeller in the shaft is I is given. The propeller rotates at omega is equal to 12 radian per second. Okay, the rotation of the propeller is given. Omega is given. Omega is equal to 12 radian per second, right? The waves acting on the ship hull induces rolling motion. Okay, rolling motion is induced, shown in the figure. So this is how the rolling motion is there. So this is how the rolling motion is happening. Okay, with an angular velocity of 5 radian per second. Okay, the rolling motion, okay, the angular velocity of the rolling motion is 5 radian per second. So the gyroscopic moment generated on the shaft due to this motion is, okay, you are being asked the gyroscopic motion generated, right? So what is the gyroscopic formula for gyroscopic motion? Torque moment. Torque is equal to I omega p, where omega is the angular velocity of the spin. Okay, angular velocity of spin. What is omega p? Angular velocity of precession, right? So if you know what is this, okay, suppose this is a rotor, this is the rotor. So the angular velocity of the rotor is omega. Now suppose the angle, now suppose the rotor changes its position. Okay, rotor changes its position. Suppose the rotor rotates in this direction. Rotor rotates in this direction. Okay, the rotor rotates in this direction. So this becomes the angle of precession. The axis of precession and omega precession, right? But if you see in this case, the angle of spin, this is the angle of spin. This is the angle of spin, right? Because the rotor will be rotating in this direction. And if you see the rolling and angle of spin, right, have the same direction. The axis of rolling motion and the axis of spin are same. So basically there is no axis of precession here. There is no axis of precession. If there is no axis of precession, definitely the omega precession is 0. If omega precession is 0, then what will be the value of torque? The torque will be 0. So this is a very conceptual question. Okay, this is a very conceptual question. You might have made a mistake. Okay, if you are unable to visualize this properly, you have just remember the formula, right? Omega p, two angular velocities are given. You would have simply thought that, oh, such an easy question, right? You would have given the answer. But this is a very conceptual question and nice question, right? Since the angle of rolling, the axis of rolling and axis of spin of the rotor are same, there is actually no axis of precession, right? If there is no axis of precession, in that case, the angular velocity of precession will be 0. If the angular velocity of precession is 0, then the gyroscopic moment will be 0. That's all, folks. Thank you. Okay, I hope you have understood. If you have any doubt, you can comment, right? I will be very happy to solve your doubt. Thank you. Bye-bye.